Drop an ice cube in your drink and it bobs to the top. Totally normal, right? But here's the strange part. Almost nothing else in the universe does this. Melt a metal, melt a rock, freeze it again, and the solid sinks. Water breaks the rule, and that tiny rebellion is the reason you're alive. Think about what floating actually means. An ice cube floats because it's less dense than the water around it. It packs less stuff into the same space. But that's bizarre. For nearly everything else, freezing makes things tighter and heavier. Solid wax sinks in melted wax. So why does frozen water puff up instead? To find the answer, we have to shrink down way down to the molecules. A single water molecule is just 3 atoms. 1 oxygen, 2 hydrogens, joined in a wide V shape. Tiny, simple, and everywhere. Yet the secret of floating ice is hidden in that little bent shape. Here's the key. The molecule is lopsided. Oxygen hogs the electrons, so its end carries a slight negative charge, while the 2 hydrogens end up slightly positive. So every water molecule is a tiny magnet with a plus side and a minus side. Scientists call it a polar molecule. Remember that it changes everything. Because of those charges, water molecules grab onto each other. The positive hydrogen of one is drawn to the negative oxygen of its neighbor. This gentle attraction is called a hydrogen bond. It's far weaker than a true chemical bond, but with trillions of them working together, it gives water almost magical behavior. In liquid water, these bonds are a frantic mess. Molecules slide, tumble, and bump, constantly making and breaking hydrogen bonds billions of times a second. They pack in close and messy, like a crowded dance floor, disordered but cozy and tight. Hold that picture, it's about to change. Now cool the water down. The molecules slow. They lose energy. And as they calm, each one wants to settle into its most comfortable arrangement, holding hands with exactly 4 neighbors through hydrogen bonds. To do that neatly, they have to spread out into a very particular, very roomy pattern. That pattern is a crystal, a 6-sided lattice with wide-open space at its heart. Picture a honeycomb made of molecules, full of empty rooms. The molecules in ice are actually held farther apart than they were in the liquid. Freezing doesn't squeeze water together. It pushes it apart. And there's the answer. Same number of molecules spread across more space means less mass packed into each cubic centimeter. Ice is about 9% less dense than liquid water. Less dense means lighter for its size. Lighter for its size means it floats. The whole mystery lives in that open, spacious crystal. You can even see this expansion bite back. Water left in a sealed bottle in the freezer will crack the bottle open. The same force splits boulders and buckles roads when water seeps into cracks and freezes. That gentle hydrogen bond, multiplied, is strong enough to break stone. Water has one more trick up its sleeve. It's actually densest not at freezing, but a few degrees above, at 4 degrees Celsius. So as a lake cools toward winter, the coldest, heaviest water sinks to the bottom first, and the near-freezing water rises to the top. This sets the stage for something life-saving. When the surface finally freezes, the ice stays on top. It forms a lid. And here's the wonderful part. That floating ice insulates the water below, slowing further freezing to a crawl. Underneath the frozen surface, the lake stays liquid all winter long, hovering just above freezing. Now imagine the opposite. Suppose ice were heavier and sank. Each frozen layer would drop to the bottom, and the lake would freeze solid from the floor up, all winter, every winter. Fish, frogs, insects, plants, everything living in that water would be entombed in ice. There would be no escape. But ice floats, so life endures. Beneath a frozen pond, fish drift slowly through dark, cold water. Frogs and turtles settle into the muddy bottom and wait. A whole hidden world rides out the winter, protected by a roof of ice, all thanks to one lopsided little molecule. Scientists think this quirk may matter far beyond Earth. Moons like Jupiter's Europa wear a thick shell of floating ice, and many researchers believe a deep, liquid ocean sloshes underneath. If life exists out there, it may be sheltered by the very same rule: floating ice as a roof for alien seas. So next time an ice cube clinks in your glass, give it a second look. That little float is a clue to something profound, that the most ordinary substance on Earth is quietly extraordinary. A bent molecule, an open crystal, and a planet's worth of life kept safe beneath the ice. If that gave you a little jolt of wonder, you'd love what we explore next. Subscribe to The Curious Owl for bite-sized wonder every day and keep asking why. Because the world is stranger and more beautiful than it looks. We'll see you in the next one.